Hi and Assalamualaikum. Let me explain about the Raman effect and how can be used in Raman spectroscopy. Firstly, when a sample exposed to a monochromatic light in visible region, sample will be observe the light and major portion of the light and get transmitted through the sample. However, a minute part of the light will be scattered by the sample in all directions. One can observe the scattering at the right angle to the incident beam. Incident light has a particular frequency. If the scattered light has the frequency same as the incident light, then the scattering is called as a release scattering. However, it has been observed that about 1% of total scattered intensity occur at frequencies different from the incident frequency, which is called as a Raman scattering. Raman scattering can be thought as a two-photon process. The electrons have different vibrational levels, and they are defined by specific energy differences. When an incident monochromatic light interacts with the electron in the sample, the electron absorb energy from the incident photon and rise to virtual state of energy. Meanwhile, the energy transfer formula is E equal to hV, where V is the frequency of the incident. The electron then falls back to an energy level by losing energy. If the energy loss equals to the energy of incident photon, the electron falls back to its initial vibrational level and in this process, emit another photon. Since the energy loss is equivalent to the energy of incident photon, the released photon has same frequency as the incident photon. As the frequency is same, release scattering occurs. However, sometimes electrons when losing energy from the virtual state can fall back to a different vibrational level. In this case, the energy lost by the electron is different than the energy absorbed from the incident photon. As the result, the photon emitted by the electron has energy different than the incident photon. This gives rise to Raman scattering. Depending upon the final energy of the electron or final vibrational level of the electron, Raman scattering can be separated into Stokes line and anti-Stokes line. If the frequency of the scattered photon is less than the frequency of the incident photon, Stokes lines are observed on Raman spectrum. This happens when electrons absorb the energy. Similar, when frequency of emitted photon is greater than incident photon, lines are observed. This means that the energy is released by the electron. The Raman spectra give the molecular fingerprint and it is different for different molecules. By studying the spectra, one can identify the rotational level and those of particle molecules. This helps in performing qualitative analysis. Similarly, the intensity value of a particular Raman line helps to determine the concentration of a molecule in a sample.
Assalamualaikum warahmatullahi wabarakatuh. Today I would like to explain about the laser Raman spectroscopy. So in this topic, we want to highlight some topic about the laser Raman spectroscopy. Firstly, we want to explain about the difference between the Raman and infrared spectroscopy. Secondly, we want to discuss about the advantages and disadvantages of the laser Raman spectroscopy. So thirdly, Why the laser is used in the laser Raman spectroscopy? Differences between Raman and infrared spectroscopy. Raman spectroscopy. It results from scattering of light by vibrating molecules. Raman results from change of polarizability. Sample preparation is not very elaborate. It can be in any state. Cost of instrumentation is very high. Next, we proceed to infrared spectroscopy. Infrared result from light absorption by vibrating molecules. Infrared result from changing dipole moment. Sample preparation is elaborate gases sample can be used. Comparatively inexpensive. Advantages of laser Raman spectroscopy. It is simplicity method. Laser Raman can detect organic and inorganic materials. Limited or no sample preparation is needed. Next, water does not cause interference and can be used as a solvent. So next we proceed to disadvantages of laser Raman spectroscopy. Laser Raman cannot be used for metals and alloys. Raman is very weak, which leads to low sensitivity. The detection needs a sensitive and highly optimized instrumentation. Laser Raman quite costly depending on their applications. The presence of impurities can hide Raman spectra. Next, heating through intense laser can destroy Raman spectra. Why laser use in Raman spectroscopy? Lasers are used as a photon source due to their monochromatic nature and high beam flux. In the visible spectral range, Raman spectrometers use notch filters to cut out the signal from a very narrow range centered on the frequency corresponding to the laser radiation. Light from the sample passes back through the microscope optics into the spectrometer. Raman shift radiation is detected with a charge coupled device CCD detector, and a computer is used for data acquisition and curve fitting. These factors have helped Raman spectroscopy to become a very sensitive and accurate technique.